This engine doesn't stay in one category. It starts like a jet and ends like a rocket. Most engines are built for one environment, air or space, not both, because the conditions are completely different. Jet engines rely on oxygen from the atmosphere. Rocket engines carry their own. Once you leave the atmosphere, there's nothing left to breathe. So systems have always been separated, until this. The SABRE engine was designed to do both. One system, two completely different modes. At lower speeds, it operates like a jet, pulling in air, compressing it, mixing it with fuel, and producing thrust. But as speed increases, everything changes. At hypersonic speeds, incoming air becomes extremely hot. We're not talking warm. We're talking temperatures that can melt components before the engine even has a chance to use the air. So before anything else happens, that air has to be cooled, and it has to be cooled instantly. The system uses a pre-cooler that drops the temperature of incoming air from extremely high levels down to manageable conditions in a fraction of a second. Thousands of degrees, reduced almost immediately. Without that step, the engine fails before it even starts producing useful thrust. But cooling air that fast introduces another problem: moisture. At those temperatures, rapid cooling can cause ice to form. And ice inside an engine moving at those speeds is not something you want. So now the system has to manage temperature without freezing itself, all happening in real time, at extreme speed. And then comes the transition. As altitude increases and atmospheric oxygen drops, the engine switches, no more relying on outside air. Now it becomes a rocket, using onboard oxidizer to continue producing thrust where traditional jet engines would stop working. Which means the same vehicle can take off from a runway, accelerate through the atmosphere, and continue into space, without staging, without switching engines. Just one system adapting as conditions change. But this kind of flexibility comes with complexity. You're not optimizing for one environment. You're balancing two, which means every part of the system is operating near its limits. Temperature, pressure, airflow. All of it has to stay controlled across completely different flight conditions. And if anything falls out of range, the system doesn't degrade slowly, it fails fast. Now think about what that changes. Traditional launches rely on rockets that carry everything from the start. Fuel, oxidizer, structure, all of it. Heavy, limited. But if a system can use atmospheric oxygen for part of the flight, it reduces what has to be carried on board, which changes efficiency, range, and design. And suddenly, the idea of reaching space doesn't start with a vertical launch. It starts on a runway.